here today to tell you guys about some of the projects we do here at Northwestern University in my group. And thank you for being here this evening. I'm sure you had better things, either 6 o'clock Central, 7 o'clock, another time zone. You could be drinking a nice wine or a beer and not having to listen to Omar talk about his muffs, but I appreciate you being here today. This is the group of people who actually do the research. Obviously, you could see this picture. This is pre-COVID. If I show a picture like this during this time, I should be fired. These are the people who do the research. I am here, their spokesperson, telling you about the wonderful things they do. Without the funding, I wouldn't be here, but I wanted to make sure I acknowledge the right people just in case if we don't have time at the end. Today, as you heard from the introduction, I will be talking about metal organic frameworks. Just to put everybody on the same setting, these materials are made from metal ions and metal clusters, organic ligands, struts. We don't really make supermolecular assemblies. We make three-dimensional materials. I personally decided to build a career on these materials. You have a periodic table to pick from, and you have hundreds or thousands of organic linkers with different functionalities. And at that point, it really becomes a matter of how do you put these organic linkers and these metals together in a programmable fashion. And I would argue that these materials, and happy to discuss during Q&A, that because of the programmability and the self-assembly, they are very scalable. And there is a startup company that was mentioned, we started it in 2014, that they could make these materials at almost a metric ton scale. This is a simple reaction in my group. This is about a kilo, just to show that, you know, nothing special about MOFs. There is a lot of things special about MOFs from properties, but from a synthesis, you put everything together, you mix them, everything dissolves, and under the right conditions, they start to crystallize. And what are you seeing here? Almost a kilo of almost single crystals of this particular MOF that is growing. And I'm not arguing here that every MOF can be scaled this way or the synthesis as simple as what I'm showing here, but in my view, most can be under the right conditions. Because you have a huge number of building blocks from the metals, from the organics, then you know, you have an enormous number of possibilities and combinations. And because of that, that allows you to have a diverse materials with diverse property from physical aspects, chemical aspects, that you could tailor them for specific applications. And we will tackle some of those applications tonight. More importantly, this family of material, what sets it aside from other families of materials is the ability to get the crystal structures, which allows you to know what you have down to the atomic level. That's unusual for a lot of porous materials. Just for simplicity, I want to show you how these materials look like when they come out of the oven. But for the rest of the talk, I will be showing you the smallest repeating unit, and which is, you know, really diving into that crystal from the micron size into the nano regime. That's what you see, the smallest repeating unit. But please keep in mind that these materials are not supermolecular assemblies. These are three-dimensional infinite network. In the Farha group here, we are really a synthetic group at heart. The applications we tackle, we go after gas storage and gas purification. Same thing, chemical purifications, water purifications, removing metals, heavy metals, removing organics. Also, we are tackling on the other side catalysis in general through synthetic catalyst for the detoxification of toxic agents such as nerve agents or mustard gas, going after catalysis that the DOE cares about, and we'll talk about some of that tonight. enzyme encapsulation, which is the subject of tonight's talk. And I will start with the Department of Defense type of application, but I will close the talk to show you how we could really taking these materials toward making fuels. And that's that's why we are here, energy and fuels, how we connect everything together. And there is also, we go to the part of the periodic table that most people forget about, which is the actinides. We love the heavy elements. They are intriguing, interesting, complicated, but at the same time, they are full of surprises, which that's why we like to work on that part of the material. For tonight, I want to concentrate on one topic. This way I don't bore you and I don't lose you. We got to concentrate on enzymes and MOFs and how those two different types of materials can get together and make a better material than the individual components. We all know what enzymes are good for. They are awesome catalysts. They are highly specific, high selectivity. Turnover frequencies are hard to compete against. But for most enzymologists, when you guys talk to them or hear them talk, they always talk about turnover frequencies. Why is that? Because turnover numbers, these enzymes under harsh conditions, they quit very quickly. They are really good at the turnover frequency, really lousy at turnover numbers. The idea in this research in my group is, how can we maintain the turnover frequency? Why now we accelerate or we get the turnover numbers that hard to compete against? And if we could do things like the way catalysts or enzymes does it at ambient temperature and ambient pressure, that's where you get your energy savings, and you don't have to do that reaction at 100 bar and 300 degrees if you could do it at at ambient pressure and ambient temperature. But there is challenges with these enzymes. They like to be in their cozy environment. If you change the pH a little bit, the temperature, you dehydrate them, they denature, and they stop working. The concept is, if you could really stabilize these enzymes under harsh conditions like high pH, low pH, different high temperatures, then you'll be able to go tackle applications all the way from water purification to generation of fuels. So our concept is, can we immobilize these materials or these enzymes in MOFs? And by the way, this is not a new concept by any means. There is not even one solid state support that has not been tested for immobilizations of enzymes. And you might ask yourself, okay, if it's been tested for everything, has it been successful? And why MOFs are different? And hopefully I will be able to answer those questions during my talk. And there is multiple ways to immobilize enzymes, and we do a lot of them in my group as well. But again, to simplify it further, we gotta concentrate tonight on channel type MOFs. Why is that? The concept when we started with this project about 6-7 years ago, can you really synthesize a MOF that has two channels? One channel is larger than the other, but they have a communication windows or channels between those two one-dimensional channels. And this is what I would call a hierarchical system. We want the large channel. This way we could really now put the enzyme only in the large channel, but the enzyme is too large to fit in the smaller channels. But the substrates and the products can come in and out through the small channel, through the windows, do the reactions and exit without having to deal with diffusion limitation by going through the same direction of the same channel. This is what I call here PowerPoint chemistry. The question is, how can we now make such a system? Here, what I'm showing you, the closest we could do. Can we have something is about a triangle and a hexagon? The triangle can be about 1.2, 1.3 nanometers, the hexagon between 3 and 3.5 nanometers, and there is windows between them. Now the question is, how can we translate this beautiful PowerPoint chemistry structure into reality? But before I tell you, we want to also, if we're trying to stabilize enzyme under harsh conditions, our support better be stable too. We can't go make a support that is as lousy as the enzyme before stabilization. And that's why here we decided to go after zirconium-based MOFs. So this one here is a zirconium-6 clusters. What does that mean? 6 zirconium ions. It's like a tiny piece of zirconia, nano zirconia. When I say 12 connected, it means I have 12 carboxylic acids capping those 6 zirconiums. So this would be a perfect structure. And we'll talk about in a little bit what does that mean if we go to low connectivity, but let's wait until we get there. If you go to the CCDC, you'll find out zirconium-6 clusters are, in discrete fashion. They exist in multiple connectivity. Okay, I told you about the 12 connected. That means you have 12 carboxylic acids, but you could put those 12 carboxylic acids in different ways in this geometric objects, and you could make them as different building blocks. 10 connected, it means you have only 10 carboxylic acids and still zirconium-6. In order to balance the charge, for every missing carboxylic acid, you will have a water and a hydroxyl balancing the charge all the way to 4 connected. You could even make a square in directionality point of view with 6 zirconiums. You could, and if you're gonna go from a geometric entities to a chemical entities, that's how they would look like. And these are the formulas. With the organic ligands, we could play the same game. From 2 connected, that means you have 2, let's say 2 carboxylic acids, 2 pyridines, 3 connected, 4 connected. But now once you got, and the 4 connected can be a simple square, a tetrahedron, or if you go to the 6 connected, can be an octahedron, can be a benzene-like. So now we could start thinking about those geometric objects and convert them into chemical entities as you see in these few ligands. So now if we want to build that CSQ topology, the triangles and the hexagons, you need those cubes and those squares. So a few years ago, we decided to use this pyrene tetraphenyl tetracarboxylic acid as the square because you have the 4 connectivity, and this 6 is, the 8 connected zirconium cluster. And if you do that, you could start getting, these are crystals. You could see we could get the crystal structure. We could make plenty of this MOF and the ligand, and that's the crystal structure of this material. So what I'm showing you here is not a chem draw. This is an honest to God crystal structure, and you could see the hexagons and the triangles. And on the side here, this is the walls between the hexagons and the triangles, and these are the windows that you get to communicate between the hexagon and the triangle. This is just a movie. I'm not sure how fast it is over Zoom, but when you zoom in, you could see the hexagon, the windows, and the triangle on the other side. Because we are not enzymologists, we wanted to start with a simple study case, and we decided to use cutinase. It's more important than anything else. It's cheap. We could buy it from Aldrich. And we could put it post-synthetically into the MOF. Obviously, this is a rendering, not a crystal structure. I wish it is, but it's not. How do I can convince you that the enzyme in the hexagon only and not the triangle? And how do we do the synthesis? Is really after we make the MOF and we make sure that we are under the right conditions. We know the zeta potential of our MOF. We know the zeta potential and the surface charges of the enzymes. And under the right conditions, we could immobilize these materials. Just to, because it preemptively answered this question, people tell me, if these are once, one-dimensional channels, when the enzyme goes in, does it leach out? And the answer, up to 6 to 9 months, it does not. Why is that? Because we chose the right, surface, charges with the right charges inside our MOF. And once it goes in, it's cozy and it doesn't like to leach out. Again, how do we know that we actually can get the enzyme into the whole entire crystals? We could actually tag the enzymes with a chromophore and watch the enzyme go inside these crystals. You could see the smaller the crystals, the faster the diffusion, no surprises. But more importantly, if you could pay attention to the diffusion, you could see that is only coming from the two ends of the crystals, but not the sides of the crystals. And that makes perfect sense because the large hexagons only from the inside of the crystals and the windows from the sides of these crystals on this side here. That means the enzyme should not diffuse that way. Here we do PXRD, and that means our structure is still intact. So how do we know that our enzyme actually inside the hexagons and not the triangles? So we do nitrogen isotherms. For the people who are not familiar with nitrogen isotherms, we do the uptake of nitrogen at 77 K with respect to pressure. So here, what you see that the black curves of this particular isotherm, that's before we put the enzyme inside our material. And you could see this step around 0.2 P over P naught, and that's a signature of a 3.2 nanometer channel. If it wasn't there, there is a problem. From this nitrogen isotherm, you could extract three pieces of information: surface area, pore volume, and pore size distribution. And that's what you see in the bottom. Those are the pore size distribution. So if you take the trace, the black trace of the nitrogen isotherm, and extract the pore size distribution, you will get the black trace in the bottom, and that shows that you have the hexagon and the triangle, the small and the large channel. Now when we put the enzyme, you could see the reduction only happens from that large channel, but not the small channel. The small channel stays the same, the pore volume did not change, and only the pore volume reduction came from the large channel. So that's indirect evidence that we really have it in the hexagons, not the triangle. And by the way, it's not surprising. It should not fit in the triangle anyways. This particular enzyme does this reaction. It takes this ester into the acid and the phenol. And this phenol, we could follow it by the UV vis. And this reaction works well. This is the background. And when we filter them off to make sure that we're not having anything leach, everything looks good. There is no catalysis. With the composite, we have a great catalysis. But that's not the whole story. So the question is, did we stabilize that enzyme? First of all, this enzyme likes to be around detergent in order to not allow it to aggregate and precipitate. You could say if we don't add detergent to the reaction, our composite is better than the free enzyme. But it's better, but not as better by orders of magnitude. So that's nothing to brag about. Now, let's add urea into the system. Urea is really the kiss of death for enzyme. It breaks those hydrogen bonding very quickly and denatures them. And you could see the free enzyme is dead from the beginning. Our composite keeps going. We could now start adding acetonitrile, THF, organic solvent. Our composite keeps going. More importantly, now we could start filtering our composite and reusing it. And remember, every time we use it, that's more turnover numbers. That means we're keeping the turnover frequency and we're increasing our turnover numbers. The question was here, did we really get lucky? How do we know that our hexagons, triangles is really the optimal material? So what we did, we went and now we made 4 different MOFs. They all have hexagons and they all the same size. Some of them have triangles and they all the same size. And some has the communication between the channels and some don't. So we want to test what's the effect of the triangle with it and without it, and the effect of the communication between the channels with it and without it. We make all the 4 MOFs and we test it. But before I get you there, I want to just spend 30 seconds here to tell you about, so what's the effect of the enzyme sitting inside the channels versus on the outside of the crystals? And we did not want to really address that question. So what we did, we cleaned the surface. How do we do it? This is a typical, it's called trypsin digestion. This is an enzyme, a large enzyme that cannot fit into the channel. Its job is just to go chew up other enzymes. So you clean up the surface. This is what most biologists use, nothing special here. Then the second thing you should ask, how can you compare those different materials? What we gotta compare is what I would call accessibility, not reactivity. Because something might be still alive, but if I can't access it, I would not know if it's dead or alive. So with this chromophore, it's like a titrant. It goes and it binds with the phosphate head to the active site of the cutinase, releases this chromophore, and since it's not a catalyst in this respect, for every chromophore, that's one active enzyme. Then we start counting the enzyme. To cut to the chase, these are the two best materials. If you have hexagons only with channels, and if you have the triangle and the hexagons with channels. So in black, that's when we put the enzyme at the beginning. In red, that's after we clean up the surface. So you could see when we have hexagons only, we could put twice as much enzyme. That's not surprising because we cannot put any enzymes in the triangles, so that's fine. More importantly is accessibility. Look at the one with the triangles and hexagons. The blue is almost 95% or more of the enzymes are accessible, versus if you only have hexagons and no triangles, only less than 10% of these enzymes are accessible. That means only the enzyme by the windows that the molecule can reach are active and accessible. The rest of them in the channel, we cannot reach them. So in this case, it doesn't matter how much enzyme we could put, we cannot really reach. So that's good. So that means we know how to make it. We know how, that means the topology is good. To move forward, let's go into a more important enzyme. This enzyme here is what degrades nerve agents. The first thing you see that NU1000, the cavity is too small to fit this enzyme, but the nice thing is we could go now extend the linker and make an isoreticular structure. That means everything is identical to the first structure, except now you have larger channels. And we do the same thing. I don't want to bore you. I showed you how we could characterize these materials in the first project. Trust me, we do the same thing for all the projects. This is here the reaction, and in this case is not the nerve agent itself. This is a simulant, because that's all we could use at Northwestern University. We use the simulant, and you could see in red we have two signals for the phosphorus that they are disappearing, and the product hydrolyzing this PF bond, which that's how you kill nerve agent, by hydrolyzing this PF bond, the reactive bond, into a less reactive bond, and now it takes it from something that can kill you to something that it does not really harm you. That's fine. Does it work well? So this is here what I'm showing you, the catalysis. This is the background. This is the free enzyme, and this is our composite. When I show this slide, I always say there is good news and bad news. If you have 30 minutes to wait, yeah, our reactivity just as good as the free enzyme, and I will show you later that we are able to stabilize it further, but our initial rate is so much worse than the free enzyme because we have a diffusion barrier. Things have to diffuse into the channels and come out, and we have to address this, and hopefully I will show you how we address it in a couple of slides. But how about the stability? The DOD wants to know, are these enzymes are stable at high temperature? So here we take the enzyme at different temperature, we soak it for 20 minutes, 30 minutes, then we do the catalysis. And what do you see? Actually, after a while, the free enzymes start to die drastically versus the composite is doing much better. More importantly, the DOD wants to know how these materials behave in the solid state. If you take the enzyme itself and lyophilize it, versus our composite, filter it, put it at room temperature, and every day measure the catalysis, I don't have day 4 here, but day 4 showed that our composite did not get affected versus the free enzyme is completely dead. So beside we could get the same reactivity at, if you wait 30 minutes, we stabilized it drastically. This is now the actual agent. This is in collaboration with the Army labs. And when we tested it, it works really, really well. And here what I'm showing you, day 0 and day 10, they are within experimental error. And you could see day 7 is going down. We're not really losing activity because at day 50 it went up. This is just different technicians and different days. This is just human error at that point. But I like to put all the data here. This way you could see that between day 0 and day 50, the composite cell reactive. The question is, how can we make it better at the initial rate? You could do that by 2 means. One, make those triangles and those windows larger. This way the agent can diffuse faster, or make the crystallite smaller. We went and we tried to do both with this new MOF. It's called NU1003. We do the encapsulation of this material the same way. And now we are able to make crystallites all the way from 300 nanometer to about 10 microns. You could see here the PXRD, everything looks the same regardless what the particle size. More importantly, the nitrogen look the same. That means we are making the same material, except we are modulating the particle size. Now the question, how does it work? If you look here, this is the background, and this is the free enzyme. If you have a 5 micron crystal, it's slow. If you make the crystallites faster, it's smaller, it gets faster. Smaller, faster enough. When you go to the nanoparticles, now our composite actually, and by the way, just for clarification, those, how I say, lines are not kinetic plots. Those are just to aid your eye to see which data goes with what. But you could see here, when we go to the 300 nanometers, actually our composite is even faster than the free enzyme. I was surprised actually when I saw this. I made sure multiple members in my team repeat this experiment, and it's good. Then we send this material to the Army labs, and they actually found the same thing, that our composite, when you have the nano regime and you remove diffusion problems, it's also 3 times faster initial rate than the free enzyme. Happy to discuss this during Q&A, why we think that's the case. So now I was really talking about taking an enzyme and a substrate, and that's it. For a lot of the reactions that people are interested in, it's beyond just that. You really need to have also a coenzyme for the reaction to take place. You need the enzyme, the coenzyme, in order for something to work. So we decided to use, as a study case is LDH. And LDH, it likes to take pyruvate to lactate. And this large molecule here is the NADH, is the coenzyme. And you could see this is really large, not a small nitrogen or a CO2 molecule. And this is a very well-studied mechanism that you need all 3 components for it to work, the right way. This is just putting the size of that molecule in perspective. Obviously, the easiest way is just keep expanding those linkers and make a larger and larger MOF. But trust me, for the MOF people on this talk, they know that's not as easy to do, because if you have a molecule, let's say a ligand, that is square with 4 arms, like the ones I showed you, the pyrene tetraphenyl tetracarboxylic acid, keep extending those arms, it doesn't guarantee that you will make the CSQ topology we want, because it has 6 options to pick from. In the last few years, we learned that those 4 options actually are the kinetic products. That means if you heat the reaction high enough, you could get away from those. But the nightmare is between the CSQ and the FTW. How do we differentiate by them? is we learned that the torsion angle around the phenol that has the carboxylic acid and the center of your linker matters. What does that mean? If you have a linker that torsion angle is 0, you will get the FTW. If you have a linker that the torsion angle is between 55 and 65 degrees, in collaboration with Fraser Stoddard, my colleague, we were able to make all this ligand with the right torsion angle, and we were able to make, you could tell without actually getting a crystal structure, this is not the box-like topology. Look here, the crystals are different. You see, they are box-like. That means you could tell this is the FTW, and these are the hexagon-likes. This is the CSQ. That's nice. We could also do STM and make sure that we have the right material, but we actually have crystal structures. That means we could compare that the bulk of the material is as pure as the single crystal. Now, these are the MOFs we made. This is the first one I showed you. NU17, 1007 is the largest. Now we go from 3 nanometer to about 7 nanometer hexagons. The triangle is about the same size as the old hexagons. So you could see we really expanded this structure drastically. And these are the nitrogen isotherm of this material. What I'm showing you here on one slide, that took about 2 years worth of work. So now we do the catalysis. And how are we going to test which MOF works better for that LDH and the coenzyme? We could use, we take in pyruvate to lactate, and we could use this non-fluorescent molecule, and when it reacts, it becomes fluorescent and it doesn't go back. That means we could start counting the fluorescence, and that's how can we start distinguishing between the two different MOFs and, you know, the initial rates. Here, what I'm showing you is the blank without the catalyst, which is the enzyme, and here, everything in solution. This is the homogeneous. If you take our 3 smallest MOFs, you know, they are not as good as the free enzyme. If you remove the diffusion and make large channels and have now both the substrate and the coenzyme diffuse, we get materials that they are more stable, but beside that, they are more reactive than the free enzyme as well. So that's nice. What I showed you is we could only take the NADH to NAD+. That's not good. That means for every pyruvate to lactate, we get to kill that many carbons. The question, if we want to use it to make a fuel, we cannot afford that. So we needed to be able to make also the coenzyme run back and forth catalytically. So in this case, I'm showing you here some pictures from what's happening really around the United States just in the last couple of days. This is from Louisiana. This is from California. And why I'm showing you pictures of disasters, to tell you that climate change is one of the top priorities, or at least of, you know, the young generations. And that's why we decided to test that hypothesis and building on what I showed you so far with taking CO2 to something useful. And here we gotta use an enzyme called formate dehydrogenase that it's take this CO2 to formic acid, with the idea going forward, we wanna take it all the way to methanol. And how we wanna do that to start with, we wanna do it electrochemically. If we take an FTO, we put a zirconia on it, we could put now this ruthenium complex. It's an electron transfer that it has the opportunity to actually take NAD plus to NADH and cycle it with the enzyme. And the enzyme can take CO2 to formic acid. And now here we're using the electrode, and we are using some electricity to generate not just the enzyme, to generate the cofactor as well and run it that way. Here, just to show you that if we don't run any potential, there is no reaction. If we run a potential, we could generate the NAD to NADH very easily. And more importantly, the composite at different pHs is a lot more stable than the free enzyme. And if we put everything together, you could see the components and the background doesn't do anything, and the composite actually works quite well. These are 10,000 or more turnover numbers that the enzyme cannot even get close to that in the free enzyme. But at the end of the day, we are using electricity, so we decided to push this a little forward. How about if we use the chromophore that we are using as a ligand for our MOFs to actually do energy transfer and run that reaction that way? It's still the ruthenium complex and it's still the same enzyme. And how do we attach that ruthenium complex? Is really because we have empty space on the node. It has a carboxylic acid that we could attach it easily. And with collaboration with my colleague Mike Wasilewski, he could do the time-resolved fluorescence intensity, and he could show that in ruthenium inside our MOF, it really has the shortest electron transfer between the ruthenium and the chromophore to run this reaction efficiently. Here to show half of the reaction, that means we are able to regenerate this NAD to NAD using light. In this case, it's just 341 nanometers. But also now when we coupled both sides together, that's what you see here. We are generating now formic acid. If you have the control with nothing, you don't see hardly anything. And with our complex put together in the right way, not just the components, this material works quite well. This has about almost 850 turnover frequencies per hour with a lot of turnover numbers. And I would say it's one of the fastest systems out there. So I hope I was able to show you that we started with just the concept, can we stabilize enzymes in MOFs under harsh conditions? Then we did some, a lot of synthesis to make sure that the diffusion there is no limitation, make sure the channels are large enough for us to be able to get things to diffuse in and out. And I ended it with, and that's where we are right now, taking certain enzymes to make formic acid, but our target is really, we want to have a cascade of enzymes to go all the way to methanol. With that, I would like to thank you for allowing me to speak here for the last 40 minutes or so, and happy to take any questions.